Yeah, so let's go ahead and stop this clip. I think we all know what's about to happen here. If I were to hit play, I would come crashing down and hit the water like a rock and probably end up with a red stomach and some pain. But the question is, why? Why do we fall like this? The answer is a deceptively simple 7-letter word called gravity. But what exactly is gravity? What is the actual reason for us being stuck to the ground like this? And how does this thing called gravity affect things other than just belly flops? These are some of the big questions some famous scientists have asked throughout humanity's history, besides the belly flops. And in this video we are going to go into a couple different explanations describing the schools of thought of gravity and where we are today. So let's go ahead and get started.
Gravity at its core is the attraction between two objects. The greater the mass of the object in question, the greater the force of attraction of this object. And since Earth is the greatest object near us, it exhibits the greatest force of attraction on all of us.
So the first person to question this theory of gravity was English mathematician Sir Isaac Newton. In 1687, in his famous publication, Philosophiae Naturalis Mathematica, or in English, the Mathematical Principles on the Philosophy of Nature. See, Newton described the law of attraction between two objects, summarized in an equation.
Now, this equation is Newton's most famous equation, and it's used to calculate the force of attraction between two objects. Now, this equation is divided into three main parts: the force of attraction, the gravitational constant, the mass of the two objects divided by their distance squared. Now, the gravitational constant was known that it existed by Newton, although it wasn't calculated until over 100 years later. Overall, this may look a bit complicated, but if you look at it figuratively, you can see the two masses m1 and m2 separated by a distance r, exerting a force of F on each other. You can think of this as the Earth-Moon system separated by a distance r. So these are the two parameters you have, and using those you can figure out the force of attraction.
While Newton's formulas are still used to describe forces and how objects behave in physics, his ideas on gravity weren't perfect. To begin with, Newton had no idea what gravity was. Newton stated in Principia, gravity must be caused by an agent acting constantly according to certain laws, but whether this agent be material or immaterial, I have left to the consideration of my readers. On top of that, Newton assumed that gravity was an instantaneous force. In this example, we have a small portion of our solar system. Newton believed that since gravity was instantaneous, if the sun were to tragically disappear, the planets would immediately fly off their orbits and go off into space.
The first person to refute this idea was a man named Albert Einstein in the early 20th century. Einstein theorized that all objects in the universe had an upper speed limit, which was the speed of light. And if this were true, that would mean that gravity as a force could not be an instantaneous force. He documented his theory in his paper called The Foundation of the General Theory of Relativity. For example,
So Einstein's idea of gravity was that gravity depresses the fabric of space-time. And so in this demonstration, this apple can be any mass in the solar system. So as the mass of the object interacts with space-time, it causes this metaphorical well. So as I retract the object, space-time itself is flat by nature. And so the bigger the mass of the object, the greater this metaphorical well is. So any questions, anyone? Yeah.
So how do we actually prove Einstein's theories?
So in the Physical Review Letters, on September 14th of 2015, a team at the Laser Interferometer Gravitational Wave Observatory actually had a signal of two massive objects coalescing, causing gravitational ripples in the fabric of space-time. Yeah, Kevin.
Well, in a recent article published in 2016, Dr. Prakash found that on December 26th that there was actually a presence of gravitational waves found as well from the same observatory as well.
Oh, good job, Kevin.
And this is where current gravitational research is headed.